All right, so let's. I'm going to give you one more example. I'm not going to throw up all the insight into that, but I want to give you another example of a prodrug. So I talked, excuse me, I talked a little bit about heroin, right? How heroin is a prodrug. And heroin is diacetylmorphine. It's morphine with two acetyl groups attached. And so it's able to penetrate the central nervous system, and then when it penetrates the central nervous system, the acetyl groups are cleaved off by enzymes in the CNS, and it becomes morphine, and now you have a whole bunch of morphine right there in your brain. There's another drug, and this is a drug for Parkinson's disease, which is a relatively common thing that we treat. And in Parkinson's disease, one of the problems that we have is we have cells in the substantia nigra of the brain, okay, in the cerebellum as well, have a dysfunction, and we actually have decreased levels of dopamine in those particular areas. Okay, that's one of the major issues with Parkinson's disease. So I think the reasonable question to ask is, hey, why don't we just give somebody some dopamine in the IV, right? If we give them IV dopamine, would that fix their Parkinson's disease? What do you think? No. Why not?
Blood-brain barrier.
The blood-brain barrier. Dopamine cannot penetrate the blood-brain barrier. You need something very lipophilic, okay, that can penetrate the blood-brain barrier. Dopamine can't. And of course, the reason that we can't ingest dopamine or take dopamine entirely is you have monoamine oxidase, okay, that will metabolize that, deactivate it before it has a chance to even get into the circulation. So what we do is we modify dopamine, and we modify dopamine into what's called a prodrug, okay, a prodrug of dopamine, and I'm just going to show you the chemical structure. And you've noticed that I've been drawing a lot of these benzene rings, right? A lot of these substances have these benzene rings, and so it is a pretty common thing here. So let's talk about dopamine. All right, there we go. And I have a carbon here, and a carbon here, and then coming out, imagine coming out at you, coming out of the board at you, I have an amine group here, all right, and then I have a bubble bond O there with a carbon and H. Okay, so I have something like this. This is not dopamine, okay? This is not dopamine, but rather this is a medication called levodopa, or L-DOPA. Levodopa is able to penetrate the blood-brain barrier, and once it penetrates the blood-brain barrier, it is bioactive, it's biotransformed into its active metabolite dopamine, and dopamine just happens to look like this. Cleave that carbonyl, the carbonyl group off of that, and I've turned that into dopamine. Very similar, very similar. And this is the active metabolite of L-DOPA. Okay, it can penetrate, L-DOPA can penetrate into the CNS through the blood-brain barrier, and then it's turned into dopamine once you get in there. And you have heard of the term catecholamine. You guys are familiar with catecholamine? And these include things like epinephrine, dopamine, norepinephrine, okay? And what makes a catecholamine is you basically have three things. You have this big guy here, this aromatic ring, or a benzene ring, or what we call a catechol nucleus. Okay, that's one thing. Catechol nucleus, you have a hydroxyl group here, hydroxyl group here. So you have 2 hydroxyl groups that are coming off the catecholvorine. And then you have this carbon chain that contains an NH2. And what is an NH2 called? An amine group. An amine. So we call these catecholamines. So all of the catecholamines, dopamine, epinephrine, dobutamine, norepinephrine, albuterol. Albuterol has a catecholamine-like structure as well. All have this pretty much this similar structure here. And what I do is I can move these hydroxyl groups around. I can do some subtle changes to this carbon chain that comes off. And just add some subtle changes, moving some groups around can mean that these molecules have very different actions. I can make them more specific to beta-1 receptor or beta-2 receptor. In the case of epinephrine, I can have something that hits all of the adrenergic receptors. So it's really, really subtle changes, Adding and taking away hydrogen or oxygen can really change the way that a medication works. Okay, so guess what? We made it through all the metabolism stuff. Hooray! We can finally start getting into what you guys are here to do, and that is to give medications and give them safely. So I'm going to talk for a few minutes. I'm going to get you guys out here a little early because I think I've assaulted everyone. Assaulted their senses pretty significantly. I know occasionally I get a little bit of flack for letting people out a little early, but at some point, you know, I can just keep hitting you guys with stuff, and what? Who cares at some point, right? You just quit caring. You're done, right? You're done. You're overloaded. So we got through that. Now let's kind of come back down to earth and talk about, and we'll kind of reroute it and we'll be a little more relevant. So I want to make sure that you guys are okay with unit conversions, because tomorrow's all going to be about medical math and drawing meds up, getting right doses. So I want to make sure that you guys are all good with basic medical unit conversions. So in healthcare, we have two general types of units when it comes to pharmacology. We have units of volume. All right. What's the fundamental unit of volume?
Liter.
The liter, right? The metric system. So you have 1 liter. And I can break that liter up into different parts, right? So if I have a liter and I break that liter up into 10 parts, we call that a deciliter. All right? So a deciliter is 1/10 of a liter. You guys okay with that? Can I break that liter up? Let's say I break that liter up into 1,000 parts. That's a milliliter. A milliliter is 1/1000th of a liter. 1/10, 100th, 1,000th. So the metric system is all about counting to 10, right? Can everybody here count to 10? Hopefully, right? Right? So 10 deciliters is 1 liter, right? Okay? So it's all about counting to 10. 1,000 milliliters is 1 liter, okay? So I'm just breaking it up, okay? 1, 10, 100, 1,000, 10,000, 100,000, million, etc. Is everybody okay with that? How I can break things up like that? Okay. So let's talk quickly about the other unit of measurement that we use in pharmacology, and that is the unit of mass. And what is our major unit of mass?
Gram.
Yeah, the gram. Now, in the metric system, it's actually the kilogram, 1 kilogram. Okay. How many grams are there in a kilogram?
100.
Not 100. 1,000, right? 1 gram is 1/1000th, okay, of a kilogram. Okay. And then if I go smaller, let's go to 1 milligram. A milligram is how many milligrams are there in 1 gram?
Yeah, 1,000 milligrams.
There you go. 1 milligram is 1 1/1000th of a gram. Okay, so how many milligrams are there in a kilogram?
How many, what, 10,000?
10,000? 100? Let me show you how you can do this if you've never converted units. So, what we can do is, how many milligrams are there in a gram?
1,000.
Okay, so that is what we call a unit conversion. I'll throw it over here. There are 1,000 milligrams in 1 gram. Are you guys cool with that? Is everybody cool with that? So, what I can do is I can set up something known as a dimensional analysis. Okay? What I do is I set up 2 fractions. I try to make them equal to each other. And this is the basis of all of our dosage calculations. Okay? So what I do is I go to one side and I say, what do I know for a fact? What do I know to be true? And what do I want to know? All right? What do I want to know? Is everybody okay so far? So what I'm going to do is I want to know, I have 1,000 grams. All right? Is everybody cool with that? I have 1,000 grams of a drug. And I want to know how many kilograms, or how many milligrams there are. Okay? What do I know for a fact?
1,000 milligrams.
Is 1 gram. Is everybody okay with me? I know for a fact that there are 1,000 milligrams per 1 gram. Is everybody cool with me? Or everybody's following? Okay. What do I want to know?
How many milligrams are?
How many milligrams there are in
Kilogram?
not
1,000
kilograms,
grams. 1,000 grams.
1,000 grams, right?
Drug.
So I told you guys we have 1,000 grams of the drug, and I want to know how many milligrams I have available. Okay, so I want to know if I have milligrams on top here, what should I have on top here? Milligrams. If I have gram on the bottom here, what should I have on the bottom here?
1,000 grams.
Gram. Yeah. So I want to know how many milligrams I have. X is like a question mark. I don't know that yet, right? That's what I want to know. And I do know that I have 1,000 grams. Okay, so that's how I set this up. I put the information that I know for a fact. And what I know is my conversion factor. Is everybody cool with that? This is my conversion factor here. That's what I know. This is what I want to know. I want to know how many milligrams I have. How do I solve this monster of a problem here? Yeah, all I have to do is cross multiply. That's all I have to do. So, this multiplied by this multiplied by this. What is 1 multiplied by x?
1x.
1x. Fair enough. 1x. What's 1,000 times 1,000? That is 1 with how many zeros? 6 zeros, right? When you're multiplying, you have all these zeros, you just add the zeros up. So 1, 1, 2, 3, 4, 5, 6. So my answer is 1 million milligrams. Okay? So, using what's known as dimensional analysis, that's the technical term for what we just did here. Okay? I put in what I know. That's my conversion factor. What do I know for a fact, and what do I want to know? Let's do one more, and I'll let you guys go. I'll do it over here. Let's say that I have 238 milliliters. Is everybody cool? I have 238 milliliters, and I want to know how many liters that will be, okay? If I can't do that in my head, let's just set up a cross multiplication. What do I know for a fact?
1 liter is 1,000 milliliters.
So 1,000 milliliters equals 1 liter. Are you guys cool with that?
We always put the smaller one up top.
Doesn't matter.
Doesn't matter. Okay.
Doesn't matter. Small, big, as long as whatever unit is on top stays on top.
Okay.
So I started off with milliliters here, I need to stay with milliliters over here. Okay, so what do I want to know?
238 over X.
238 milliliters is X. That X is just, you can even put a question mark if that's confusing. Liters. And how do I solve this monster? Cross multiply. So 1,000 times X is 1,000 X, right? Equals, what's 1 times 238?
238.
238. Now, how do I solve this thing? I divide, and I need to get X by itself, right? So what do I need to do to this side here? Divide by 1,000, right? Because 1,000 divided by 1,000 cancels out, right? And then this X is going to fall down by itself. But what I do to one side, I have to do the other side, so I divide this by 1,000. What's 238 divided by 1,000? 0.238, and that is my answer. 238 milliliters is 0.238. Yeah, it is. Does that make sense? How to do that? It's just a know want. What do I know for a fact? What do I want to know? Now, I know there are some of you where the answer is very intuitively obvious, okay? You don't have to go through this process. That's okay, okay? I'm more interested in getting the right answer, so I'm not going to put you in a situation, you probably remember grade school, where like, write down all the steps that you, I don't care, okay? As long as you can consistently get the right answer and you understand how you arrive, do whatever. But some people in this room may prefer to do a step-by-step procedure and then do that every single time to work through the steps. That's how I work. I do it step-by-step. So either way works for me, but I just want to make sure that you guys are good and you have that tool available to you, because it'll be very helpful when we start pulling up drugs tomorrow and doing dosage calculations. Okay, so you guys okay with that? Some other calculations, some other conversions that you're going to run into in pharmacology: pounds to kilograms. That's a big conversion. Is everybody okay converting back and forth between pounds and kilograms? 2.2 what?
Divide by 2.
To do what?
Divide the weighted pounds by 2.2
Okay.
to get kilograms.
So
Half minus 10%. Half minus 10%.
half minus 10%, whatever works. So the conversion factor is 1 kilogram equals 2.2 pounds. Does that make sense? 1 kilogram equals 2.2 pounds. Because there are situations where you will have to convert from kilograms to pounds, right? And from pounds to kilograms. You need to be comfortable doing both. And depending on the situation, there are actually situations where some things are in pounds. Particularly when it comes to airway, we'll talk about some calculations where you'll need to convert the patient's weight into pounds potentially. And then temperature. Okay, there are some conversion factors out there. I'm not going to make you memorize them, but you should know what is normal body temperature in Fahrenheit. 98.6 degrees Fahrenheit. What is that in Celsius? 37. Okay. I know that 37 degrees Celsius is normal body temperature. Okay. 32 is going to be a little cool. 20 in the 20s, you're talking room temperature, right? 20 degrees Celsius, you're talking in the 70s or so. So that's pretty darn cold. So 37 is a number that you'll definitely want to know. 37 degrees Celsius is normal body temperature. 98.6. All right, cool. All right, let's see here. It's going. Oh man, we'll be going on 5 here pretty quick. Let's get you out of here. Okay. You guys feel like you've been assaulted enough?
Yes.
Yes. All right. I'll let you guys out.
Well,